Okay, well, oh, you want me to go? Ready to go? Okay. Well, thank you for coming back. Normally, people don't come back for the second lecture, so it's an honor. That's Norman. I think that's just about the end of my awful jokes. I think no, I have one more. I have one more. So that's something to look forward to. So, due to our excellent production values yesterday, we left on this cliffhanger. So we were looking at the calculation of gluon fusion through a top quark loop to a Higgs, which we saw was the dominant way of making a Higgs boson at hadron colliders. So if we understand that, we understand a huge fraction of Higgs physics at the LHC. And we saw that we could calculate it by looking at the different tensor structures. We looked at the simplest one, and we saw that it was related to a nice standard loop integral that we can get from our favorite QT textbook. And then we plotted this function that showed the change away from a effectively infinitely heavy top all the way up to the threshold where the Higgs would directly decay to two tops. And we see that if we are in a regime around here, where we zoom in on the green blob, then the effect from the top mass is pretty small, around 5%. And that was where we left off yesterday. Now, the fact that it is so small, probably tell it's okay to be recorded, yeah. That's okay, you won't be able to see my fancy logo. So the fact that it is small means we can effectively replace it by its limit, which gives us this prefactor here. There's a color factor, there's our tensor structure, and there's our polarization vectors for the gluon. Now, why is this useful? Why would we want to do this? Well, what we are, oh dear, that would have been the end of me. What we are effectively doing when we perform this limit is we're saying that the Higgs is much, much lighter than the top, which is a fairly questionable approximation. But if that were the case, then I could replace this loopy structure here with this vertex here, because if I look back over here, I can imagine this is essentially being a Feynman rule that couples my gluons to my Higgs. And that is what I can do. That is what I can do. And by making the Higgs go to infinity, the top go to infinity, I'm effectively integrating it out and resulting in an effective interaction that introduces a term that directly couples Higgs to the gluons. And for some historical reason, this is left with a coefficient of A, but I think that's less fashionable now because A is often also a pseudo-scalar. But this A is just our prefactor that is going to give us essentially our Wilson coefficient of the operator. And if we count powers, we see this is a 4-dimensional operator and this is a 1-dimensional thing. So this all together becomes a 5-dimensional term in our Lagrangian, which is, of course, highlighting this from an effective field theory. So why would we want to do that, right? That's the top is not infinitely heavy, and the Higgs is not much, much, much lighter than the top. So why would we want to do that? Well, before we do that, we have to get to what A is. We get that from our calculation, right? We already know what A is. We just calculated it. So we know it's 1 plus something else. Good. So why would we want to do it? Well, the idea is that if we expand that operator out, we get now a whole bunch of new terms, which come from our Lagrangians. We have the vertex that we just calculated, but they also have the expansion of the gluon field strengths to give us a coupling between 3 gluons and a Higgs, and also 4 gluons and a Higgs too. And we can use these Feynman rules to calculate other processes. And we can also use it to calculate QCD corrections to this process. And as we scale up the difficulty, so if we scale up the number of loops, or we scale up the number of legs, the calculations become increasingly complicated. And so if there is a dependence on the top mass in our calculation, and our lowest order in perturbation theory is a loop, then when we go to next leading order, we're going to get hit with a 2-loop calculation. And at next leading order, we're going to get hit with a 3-loop calculation. And this is not going to become pleasant very quickly. And so it's nice to have an ability to calculate higher orders in QCD efficiently and quickly. And this is what this effective field theory is going to allow us to do. So for example, so again, these numbers are now somewhat out of date, but the point is still there. So if we expand our Higgs cross-section through next leading order in QCD, then this term here, roughly 13 picobarns, is the leading order number. So that's essentially what we just calculated. Okay, we have to square it up and we have to do this thing called PDFs. Maybe you've heard of them. So we integrate that with our calculation that we've got, and we get this number, right? Now, someone that's very clever comes along and says, okay, well, leading order is fun, but let me calculate next to leading order. And they get this coefficient here, which you see that is more than 100%, right? So our perturbation theory is starting off on very iffy foundations. So the cross-section is more than doubled at next to leading order. Then I can include next to leading order, and I see it's not quite as dramatic, but still pretty big, right? So if I didn't have these higher order corrections in my theory, I would struggle to do any phenomenology at the LHC, right? So I need to have this effective field theory, at least as a first pass, to allow me to access higher orders in the QCD coupling, right? To understand the dynamics of at least the massless QCD, the massless gluons, to get me that accuracy that I can have a realistic go at phenom. And so to play devil's advocate, you can imagine what would happen if we didn't have this number here, right? If we just had some kind of Higgs-Pythia style game where we just took the leading order number and hoped for the best. So what would happen? So if we were to use just leading order, then our Higgs cross-section would be this blue line here, right? This is one of those famous, old now, but famous experimental plots where we're measuring couplings in different channels, signal strengths versus Higgs cross-section. And this is normalized to the standard model so that 1 is basically your prediction of the standard model. And if I had just a leading order prediction, then I would have essentially half of the rate in all my channels. So all of my theory would be here. And you see that, okay, apart from ones that weren't very well measured at the time or constrained, none of it agrees. So if you only had leading order, you would immediately have inferred that there was some fourth generation or there was some BSM, because the Higgs was going to have to be twice as much, right? You have to have a huge amount of cross-section you have to explain. And now when you include next to leading order, you would get to this red line here, which is better, but obviously not fantastic. And the downside of just still using next to leading order would be that you would have a huge theoretical uncertainty. Right? So this red smudge here would be a conservative way of estimating the theoretical uncertainty from higher order corrections from the Higgs cross-section at next to leading order. And you would see if that was all that we had, the LHC program, at least in terms of its Higgs physics, would already be done. Because there would be no point, I mean, okay, you can still do these ones, but essentially every measurement would already be dominated by theoretical uncertainties, because the uncertainties would be huge. So luckily, there's been many hard efforts by many people, but the big, one of the crowning achievements of the last 10 years, just sneak it in 10 years ago, was by Babis Anastasia and PhD students in Zurich. And they were able to, the first was to calculate the Higgs cross-section at n cubed alone. Now, this was a huge deal, because the story I was just telling was, oh, look at this whopping great perturbative correction. I calculated something great. I calculated the next order. Whoa, it's massive. I do it again. It was also massive. So the obvious critique is, well, okay, well, n cubed alone is probably going to, add another 50% on again. And how can you be certain that you're going to get to some number that we can tell our experimental colleagues that they have some ability to trust? And n cubed alone, so what we're looking at here is the variation in the cross-section as a function of some unphysical parameters. So the renormalization and the factorization scale varied together from some central choice, which would be 1, to be the value that you think would be your favorite prediction, and then varying it across a range from around a quarter to a factor of 4. Now, this gives you, to a certain extent, an estimate of how much of an impact your higher order corrections are going to have. Now, it is not perfect, but it's a reasonable way of estimating the perturbative uncertainty. And as you do at leading order, as you can see, there is this epic uncertainty, and even that is not quite enough because it doesn't get anywhere near the final result. But the leading order result is essentially telling you you're throwing a dart at the blackboard, and the Higgs cross-section is somewhere around 20 picobars, give or take. And then you get to the next leading order and you see this big increase, but still a huge variation, right? The scale dependence hasn't begun to asymptote in any way. And then the next leading order, which is the green curve here, it started to look very reasonable, especially if I ignore these somewhat lower end of the scales and focus on this middle band here. We see that there's not so much variation. But then finally, n cubed below, we see that it's flattened out and it lies within the green band's range. So for the first time, we hope that we have reached an element of perturbative control where if and when we calculate n fourth below corrections in the effective field theory, that they will not give us any surprises. Now, if you are a theorist and you're very formal, at this point you can wind me up and say it wasn't, accusing an asymptotic series. Eventually there should be some kind of breakdown. I know for us to fit, and I just try and run away. My car's engine's running, so I can just run for it if you ask me that question. But yeah, so as far as we hope from a phenomenological point of view, the Higgs cross-section is under reasonably good theoretical control, at least at the total level. Good. So now the question is, REFT that I just spent these last few minutes lauding and celebrating, where should we be concerned? At what point should we say, okay, well, the top mass is not infinity? So where is it going to give us grief? And okay, so the obvious thing would be if the Higgs were heavier, because then it's a much worse assumption. But luckily, our experimental friends have narrowed the Higgs mass down to a range where we don't worry about that. So what happens now is in different kinematic configurations, effectively when the Higgs becomes high energy. So if I have a loop here with an additional gluon, obviously this diagram exists in the full theory, so this exists in the standard model, and it comes in at next to leading order, right? So I delete this gluon here and I have my leading order picture. I add it in. It's part of what we would call the real radiation at next to leading order. Now, in our experimental landscape, we would have our initial state gluons colliding and our Higgs now recoiling against something. So our Higgs is now at a non-zero PT. So this will be effectively in the seen, this type of diagram is seen in the recoil of the Higgs. So you see it in the transverse momentum spectrum. Now, if this Higgs is low energy, so if it's just a low PT Higgs, then everything we talked about so far is okay, and I can integrate out this blob, and I get something which looks to within a few percent corrections, pretty good. The problem arises when the Higgs becomes sufficiently energetic that the Higgs PT is a scale which is of order of the top mass. So if the PT of the Higgs becomes comparable to mass of the top itself, then the effective field theory breaks down. And it actually breaks down in a way which is less than, okay, I don't know how things break down in a desirable way, but the way in which it breaks down in an undesirable way is that it will overestimate your cross-section at high PT, right? Because in an EFT, they tend to not be very respectful of unitarity. So at high energies, they'll give you a large correction. And what happens is the full theory result is going to overshoot, that it's going to be undershooting the EFT result. And so if we are looking at high PT Higgs bosons, we need to be very concerned about the top mass. And we can't be using about the EFT. But if we're looking at it in more of an inclusive number, where we are looking at sort of total cross sections, that sort of thing, we can be less worried about the deviations from the effective field theory. I should have mentioned as well that we can get back a lot of effective field theory, a lot of full theory results by just normalizing the effective field theory predictions by the ratio of the full theory to the effective field theory at lowest order, right? Because we have a scaling argument that we know the corrections are roughly 5%, so we can include that back in. Okay, anyway, so there's our caveat, and here's the proof. So this is one of the slides that was so egregiously old that I had to really write a new slide for this talk. So, I'm excessively lazy. So normally I would try to waffle my way out of any problems. But this one from 2018, I had, the same beautiful introduction. And then I showed it saying, hopefully one day we'll get this to next to leading order in PT. And I think I even referenced one of my dodgy papers that was some approximate version of it. But now in the intervening time period, progress has been so good that now I can actually update it, not only for give you a next to leading order prediction for the Higgs PT, including the mass at the top, but in fact an N and a low plus PS prediction, which means that this is a next to next to leading order calculation of Higgs production, including the top mass matched to a parton shower. That's a lot of technical jargon there, but the important thing is that it's a very, very good theoretical prediction. If you're an experimentalist, you can see it as having a big thumbs up, and if you're a theorist, then you already know the words probably, so it doesn't matter too much. But the important point for our discussion is validating what I said previously. So it's always good when that happens. So down here, this is the ratio of the full theory to the top, to the effective field theory. We see there's some flat correction, which I argued I could rescale in, right? There's a flat correction I can correct. I'm not too worried about that. And then as we approach the top mass, which I'm led to believe is around here, the things start to change. And in that region, the EFT will greatly overshoot the full theory result. And so if you're plotting your data against this type of thing and you didn't know this and you had an EFT prediction, you might start to get excited that you discover some new physics. But fortunately, it's just the top giving you a bit of a kicking and saying, don't forget about me. Good. Okay. So that is Higgs production in gluon fusion. Any questions on that before we talk about other topic? It's a bad time to like scratch your it's like an auction, right? You don't want to keep your hands down, right? Okay, good. Okay, so then the second most dominant production mode at the LHC is vector boson fusion. And what we said last time, and we can remind ourselves, is that we're very lucky that these two modes are the two dominant ways looking at the Higgs boson production, because we get access to the coupling to fermions through production through gluon fusion, and we get access to the couplings to vector bosons through vector boson fusion. And the kinematics of that's okay. So it's slightly unlucky because this one is so big that you can radiate two partons here too, right? And have a Higgs plus 2 jet topology that comes from gluon fusion, and that will fight against your Higgs plus 2 jet production from VBF. But luckily, VBF is very kind to us again because it gives us a very unique kinematic signature. So because you radiate these two T-channel vector bosons from the initial state fermions, they would like to effectively keep these two jets very separated in rapidity. And this is not the case for jets produced from gluon fusion, where they don't have this large rapidity separation difference. So you can set up these kinematic cuts that isolate VBF in favor of the background, which is happy for everybody. It's funny now that Higgs has gone from being our signal with one slide ago now to being its own background, but that's the way of it, right? You're only as good as your last slide. The other nice thing about this separation is that we see it's actually stable under perturbative corrections, because as often is the case, or not often the case, sometimes you have a lovely prediction at leading order, make a very clear kinematic signature, and you relied upon some kinematic configuration of the Born topology. Right? You relied on the fact that this was going here and that was going there, so then I can do this and everything's good. And then this like jokey perturbation theory comes on, like, well, actually I can radiate something and I can move this over there, and guess what? Your lovely physics is going to be completely ruined. Luckily for us in this situation, it's not the case. So the large rapidity separation is stable under higher order corrections. It's hard to radiate QCD radiation centrally in here, right? That's the good news. Good. And so VBF is our access to understanding the coupling of Higgs to vector bosons too. So that's the two main production methods of the Higgs. We now have to think about its decay. I've already tortured you with this last night, so now I get to torture you with it again. So what a win! So every Higgs channel that it can decay to, every open channel has what's called a partial width, where we just calculate the inverse lifetime for that decay, and then when we sum over all the partial widths, we get the total width. Right. So for the Higgs, that's BB bar. WW, ZZ. I wonder what the ZZ is relative to the WW. There's your PTSD. And if you want to know the branching fraction, of course, you take the ratio of the partial width to the total, and that gives you some percentage. Good. Now, for us, the 125 GeV Higgs is a real blessing because it gives us all of these different modes. It's a real experimentalist friend, right? imagine if we had a 300 GeV Higgs. You've got like two numbers, right? So the 125 GeV Higgs is a blessing for a phenomenologist. We have lots of different things to study. The main three, so the BB bar is the dominant one. Of course, WW is relevant too. These two are the discovery too, right down here. So this slide is also a bit old. But the BB, so it's mostly decaying to BB bar. That's well over 50 to 60%, depending on how you define the botany color. And then ZZ4 leptons down here. So this is really suppressed, and it gets worse, right? Because remember that the case of ZZ is around 2%. I think we agreed yesterday. But then the Z itself has to decay to something which our experimental friends are going to well measure. So the rate is suppressed again when we go to a nice 4 lepton final state. So even though gamma gamma is even further suppressed down here, it was discovered at the same time as ZZ because you don't have to pay any further branching ratios in the decay, right? When this guy decays to leptons, it drops down here again, and then gamma gamma is roughly the same. So again, yeah, so it's interesting. And even in the discovery modes, we have couplings to tops and W's that go around here, and they have couplings to vector bosons. So we learn a lot about the Higgs on those channels. Okay, so one of the oddities of the Higgs is that when I compare it to its friends, it looks a bit different, right? So these groupings of 4 are roughly the big hitters of the standard model. They're the ones with masses above 50 GeV. So, and the W, the Z, and the top all have of order of percentage width, right? So they have a width of a 2 GeV or 1 GeV. But the Higgs then has this tiny, tiny MEV width. So it doesn't look like its friends. It's the odd one out of the party. And so the question is, why is that? Right? This would have been a good question to ask last night. So we can work it out fairly quickly by looking at the various decays. So if we think about the Higgs decaying to on-shell Bs, which is always going to do, we can write down the simple matrix element here. And to get to the partial width, we just have to multiply it by this correction factor. And here is our partial width for Higgs to BB bar. So the thing that we have to remember is that the MB over M Higgs is small, so we can effectively ignore this term here. And this is the bit we're going to have in our head. So MB squared, M Higgs over MW squared. Now, if it wasn't in the evening and we wanted to do the real calculation, we can calculate the proper matrix element for decaying to on-shell WWs as follows, right? And with that, we can then put the decay width into the partial width. As this then is no approximation, this is the real formula at tree level for a decay for a Higgs to 2 on-shell Ws. So this is probably for a heavier Higgs, but it was enough to show us our point, because if we look at the scaling here, this is MH over MW, MH cubed over MW squared. So this thing roughly scales like an electromagnetic coupling times 100 GeV start mass, right? So it's going to look like of order a GeV, right? When this decays on shell, the Higgs looks like any other electroweak scale particle, and it has a total width of order a GeV or 2, right? So it would look just like the W, like the Z, or like the top. But when I don't get access to WW, I go back to my power law. I see the scaling between the on-shell widths is like this. So if I turn this one off, MB squared is always going to be killed by the Yukawa coupling, right? So if I don't have access to WW and I only have access to the bottom quark, then my GeV width is suddenly getting hit down to the level of MEV because the ratio of the bottom quark to the Higgs mass is so small. So effectively, the Higgs width is tiny because the WW decays aren't allowed. And you're only left with these bottoms ones, and they're only ever going to contribute of order a few MeV. So without W's, we don't get a big width. Here we can plot, and a plot says 1,000 words. So this is the plot of the Higgs width as a function of the Higgs mass. And as you see that, it's basically mapping out the WW rate and the ZZ to a lesser extent, is that as soon as I get access to the WW decays, I get a nice big electroweak scale width. But as I'm down here, I have this tiny little width that we have left over in the standard model. So that's why the Higgs width is so small. It's always a good elevator discussion if you're trapped in an elevator with someone and then you just start panicking because they're trapped in an elevator with you. You want to start asking about the Higgs width. Always. Real icebreaker. All right. Good. Okay. Okay, so now we have an understanding of how the Higgs decays, what are its channels. We have to start measuring its couplings, right? Because that's the job of the experimentalist, is to tell me if the scalar they have in the LHC is the same as my scalar I have in my Lagrangian. And to do that, we have to know how the Higgs couples to all of the particles in the standard model and hope and look for deviations. And so typically what we do is work in what's called a narrow width approximation. And now for the Higgs, this is going to sound like a pretty good approximation because we just said it's all the Higgs width is essentially 0. And so narrow width sounds pretty good. And when you do that, you factorize the production from the decay. So you essentially take a production cross-section for the creation of a Higgs, and then you have here, and then you decay the Higgs to whatever final state you want. And that final state we want, we know, is just a ratio of the partial width to the total width. So you effectively get the Higgs cross-section times the partial width. Now, for like the Z or the W, you might always be worried about off-shell effects, and because this is a bit ropey, but for the Higgs, it's a pretty good approximation because we saw the width is so small. So now it seems like our life will be easy because now I just go to my final state of interest and I measure it, how much of it I get, and then I collect it all together. And from that, I use this formula and I can get the couplings that I wish. But of course, the job of the experimentalist is made more complicated because this width down here depends on everybody altogether. So you can't just look at an individual decay mode and say, okay, I'm going to get the coupling of the Higgs to Z from looking at Higgs to Z to 4 leptons, because I have to be aware of how many Higgs I made in total, because it depends down here on the bottom quark, right? So that's the slight downside of our 125 GeV Higgs, is that everything depends on everything, but the dominant part of this is the bottoms, which is the hardest one to measure. So it's not all fun and games. Now, what I just said was true, but isn't entirely the whole picture, because you also can have more fun at the LHC than just working in the narrow width approximation. So we can think about how a particle behaves, and an unstable particle behaves in a QFT. Its propagator has two terms. It has this real piece here, which will be our standard propagator that we would know and love. But then because it's unstable, we have to include this term here, which gives a large complex part and effectively ensures that we can decay the particle properly. This is nominally higher orders in alpha than this, so it's a bit of an issue. Anyway, but the point is that if I am in the resonance region, so if I am colliding, if I'm making my particle close to its mass on shell, I effectively get rid of this term here, and then I get this term. I get only the width term survives, and I get back to my narrow width approximation. So narrow width approximation is just turning this piece off, keeping this piece, and I get my cross section like this, just like I said before. Right? I'm using the Z for this because there's enough data that I can show it in beautiful pictures, right? So this thing is essentially this region here, where S is pretty close to the Z mass, and it looks like the narrow width approximation. But if we look on our data, we see we have this huge number of blue events over here, where we are not in the narrow width approximation. So I'm in this rectangle here, then over here, S is very, very big, right? So if S is big, then I don't care about this, and I certainly don't care about this, right? If I make S be very, very large, then my propagator factor here is effectively just a 1 over S. So that just suppresses the cross-section as it should, but the point is that there's no dependence here, or at least very subleading dependence on the width, which means that I get a complete and utter freedom in measuring the coupling of the Z to my initial state and my final state without any worries about the global properties of it, right? How much the Z couples to other things is irrelevant in this region here, where I know what the final state is, and I know what the initial state is, and I know I'm well off the nutshell. Happy? Good. So, the question is, can we do a similar thing with the Higgs? And the answer is yes. So surprisingly, at first glance, the Higgs has a very large component from its off-shell production. So this figure here is the invariant mass distribution of the Higgs to 4 leptons. as a function of the, sorry, the M4L down here. And so this bin down here, we have our Higgs resonance, which of course is narrow width. So it's just one bin on my histogram. But if I bin it even more finely, it'd be a little delta function essentially. We have some tiny width bit here, which is our on-shell Higgs. Then we have this huge blob here that extends out here. And there's an awful lot of physics hiding in here. What drives this region here is that the decay to the Z's is going on shell, right? So I keep hitting you with this miserable Higgs to ZZ decay. But over here, as we remember, it's not very easy to make the Higgs go to ZZ because the Z is off shell, so the branch ratio to Z is only a couple of percent. But as I increase the energy of my Higgs, I move away from the resonance region, but eventually I hit the energy where I can make the Z's on shell again. And then I get a big whack of enhanced phase space from my decay. So over here, I get a turn on from my Higgs to ZZs. And, see, I'm still suppressed relative to the peak, but I've got some product cross-section back. And then it sort of turns over, but as soon as it starts to go down, it starts to meet a friend over here, which is coming from the top, right? So remember, the Higgs is made through a top quark loop. And in this situation here, I have to be not in the EFT because I'm at effectively a heavy Higgs, right, when I'm looking at large S. And so here I have to include the top again, and I have this now second enhancement, whereas it comes when I cross the top threshold. So here I have enough to make two tops on shell, so I get a boost from my loop integrals, which pick up an imaginary part in this threshold. And then after that, my physics is done, or is it? Who knows? In the standard model, it's done, and then it just decays after that. So if you integrate from here up to here, you see that there's a sizable amount of off-shell cross-section at the LHC, which is great because that gives us a second way to study the Higgs, away from its on-shell region. We can study it off-shell, and we can learn very independent facts about the Higgs. So that's good news. We can't have too much good news because we might get happy, so we have to get brought back down to Earth. The standard model, again, decides it would like to mess around with us. So the plot I showed you before was a nice simple one made by me so I could understand it. This is a much more complicated one. No experimentalists would ever allow you to have a single line on a plot, right? And that would be not be efficient enough, right? So they have to have at least 4 lines here. So we have the first one here, the black one is the one that I liked, right? That's their version of my plot. So they binned it finer than me, but there's the narrow resonance, and then there's a turn on from the 2MZ, and then we have another kink here from the top mask. But that's effectively the same thing we just looked at. The yellow line, or yellow-orange, we can debate about that as much as you want afterwards, is coming from the standard model continuum. And here, I'm assuming they're glue ones. So here, this is the GDG initiated loop, where I radiate 2 Z's from my top loop with no Higgs. Right, so I have a box diagram, glue, box, ZZ. So that also happens in the standard model, and it's not a rare process either. And this is this yellow term here. Then the pink one is what happens if I add the two together. And because they are quantum mechanical, they have the same initial, the same final state, they interfere with one another. And so the green line here is if I add the two incoherently, so I add the two yellow and black together, I get the green. That would be super nice, right? The pink is what happens if I really do quantum mechanics. And you see there's an interference between them, and it drives the cross-section down significantly at higher energies. And this is up to you now to decide whether it's fortunate or unfortunately. So if you're an experimentalist, it's unfortunate because more cross-section is better, right? Especially in this nice clean channel. You can measure 4 leptons, every day of the week. You'd be quite happy about it. So that's unfortunate. If you are the fortunate camp, would say that it's nice to live in a theory which is unitarized by the Higgs and that we don't have infinite energy and all that sort of stuff. So the theorists might be more happy that the Higgs was doing its job of unitarizing longitudinal scattering. The experimentalists might be sad, but we can at least agree that it's interesting to see this interference pattern here in the LHC, and that it's a real macroscopic manifestation of a very interesting quantum mechanical phenomenon. All right, so actually I might skip I show it to you already. So this is actually now measured. So this is one of those things where 10 years ago we were still talking about this and I was going to be great. And then I got on with my life. And then eventually I get phoned up by a journalist asking for a quote because CMS is about to publish a Nature paper. I had no idea, but they completely spilled the beans on there, saying that CMS is going to publish a Nature paper measuring this interference. And so this is from that paper. And what we can effectively see is that at high invariant transverse mass, we can get some quarks and some high invariant for lepton mass over here, where we have nice leptons. We see that the observed data lies below the prediction where there will be none of this off-shell interference term here. So this effect has now been measured at CMS, and it gives you a whole new tool with which you can play with the Higgs. So one thing you can do, which I didn't really talk about, but I can show you quickly enough, is I can use the fact that this one depends on the width and this one doesn't depend on the width to take a ratio. That ratio scales like the width. Simple enough maths. And so if I measure the ratio of on-shell to off-shell cross-section, I can constrain the width. And that's what CMS did. And so here you see, you guys know all these things better than me because you're a lot of experimentalists. But the point is that CMS have used this off-shell to on-shell ratio to constrain the total Higgs width to be 3.2 plus or minus a couple of MeV, which is an amazing result, right? It should be, this was sort of, it's remarkable that CMS and Atlas 2 have been able to measure something of MeV scale physics in a GeV, bending over thousands of like GeV, right? So that's an incredible precision result from them. But I would argue it's not even the most interesting thing you can do with this data, because to get the width, if I just take the ratio of the two off-shell and on-shell cross-sections to get the width, then I'm effectively implicitly assuming a cancellation between the couplings when I did that ratio, right? I'm coupling the GI, the GZ and the G top. I canceled it between my numerator and denominator to get access to the width. However, if I keep it in there, I can actually probe the Z coupling and the top coupling at high energies, right? So this off-shell cross-section on its own is sort of interesting because it immediately gives me access to how the Higgs talks to particles at very high energy away from its on-shell region. And so this, when we think about later on about SMEFT and measuring these couplings in regions where there could be contributions from new operators, this will be one of those regions which will be interesting to look at. So this, as time goes on, and this gets more and more finer binning and more data, this is going to be one of the lifetime plots that I think the LHC is really going to be proud of. It's going to give us a lot of physics. So yeah, it's one of my favorites. Okay, so that's, I think, the end of the reliable bit of the talk. And now we talk more about what can happen in the future. So less reliable. So, okay, is there any questions before I start waffling and completing that to Wonderland? Yep.
So that's the off-shell distribution the whole distribution, right?
Yes.
So when the scale getting higher, the mass of the Higgs also running.
So the mass of the Higgs isn't really a parameter here because it's as you saw in the propagator, it gets eliminated. I mean, it comes in, but S is much bigger than Higgs, so it comes in too, but it's sub-unit. So, but it's true they have to include the couplings at the top, right? Because the top is now a result particle, so you can't look at the EFE with these predictions. So you have to fully include the top, which makes the theoretical calculations harder. But theorists like when you say the hard calculations to do. So the predictions for this are now next to the more than GCD. And presumably there will be some, by the end of the LHC, this theory will improve somewhat too. But yeah, I guess sorry, the question was.
So the mass normalization running is not very sensitive on the final.
So you have to run the couplings. Yes. So the couplings that run will be the top mass, so the Kawasaki power, and then coupling to the Higgs, the ZZ coupling. Yes. So you would evolve them with scale. Yes. Now okay, I have to get into the nitty-gritty of the CMS analysis, see how they did that for the mass. I'm presuming that they didn't, but you see that's a sub-leading effect either way, when they're talking the level of a measurement of, with 100% uncertainty. So yes, over the long term, that's one of the things you want to do with this off-shell cross-section is run the couplings and test that running, right? But yeah, it's a fun playground because you need to worry about that sort of thing. Yeah, but my point is the mass of the Higgs is not driving this prediction, right? The mass of the Higgs is a very, very subdominant parameter in this prediction. Right? So yes, the mass of the Higgs runs, but you won't notice it. Right? What you'll notice is the top U power. Good. Any other questions? All right. Okay. So this is my loving sketch of where we are now. Because if you remember from yesterday's lecture, we said, okay, there's two parameters in the Higgs potential, mu and lambda. And the ratio of them gives us the vacuum expectation value. And so I know the vacuum expectation value because I know the mass of the Z and I know the mass of the W. And so that tells me the vacuum expectation value. That means I only have one free parameter left in the Higgs potential, which is normally written as the mass. Right? So once I have the mass of the Higgs, I know everything in the standard model. Right? And so you get it here, and you basically know that the minimum, you know the mass, so you start here. Now, the standard model predicts the shape away from it, but you haven't measured the shape away from it to see whether they agree. Right? And so what you do with what you do on sort of day one of the Higgs physics is, okay, we've got a scalar, and it seems to be responsible for electroweak symmetry breaking. And we know the minimum of the potential is here, and the mass is there, so we can draw the standard model potential. Now, what we have to do is to test the predictions of the standard model by nudging physics away from the minima and understanding how the Higgs potential looks as we move around in it, right? And if now the standard model tells you what it thinks it should be, we have to then see if that's revealed also in the data. So that's I would say the main critical question for LHC Higgs physics is the shape of the Higgs potential that we can probe at the LHC in agreement with the shape of the potential as predicted by the standard model. Now, the way you do that is by measuring the Higgs self-coupling lambda, because remember that is now a prediction of the standard model. So I tell you what I think lambda is. Now the experimenters have to go and measure that and tell me whether we all agree with each other. If they do, then we have the standard model potential. If they don't, then maybe there's some new physics that's altering the shape of this potential away from the minimum point. Right? So that's the aim of it. So how do we do that? Well, if we need access to lambda, we have to draw this type of diagram here. Right? That gives me Higgs cubic coupling, which depends on lambda. And then if I can make two Higgses, then I would have access to the Higgs self-coupling. However, if I go back at warp speed, all the way back here, if I was smart, I would have included this again, but we've established that ship has sailed. So it better be worth it. Here we go. I have to go down a long way before I find di-Higgs. So di-Higgs is a very hard process to measure at the LHC or any collider because it's an electroweak correction to Higgs production, and so it's suppressed by 2 orders of magnitude. Now, at least at 100 TeV, it's cheap to make a Higgs in the final state, so the suppression isn't quite as bad, but it's still pretty bad, right? So that long trip back through the slides was for a very miserable point. It's a real shame. Okay, so warping back through. There we go. Okay, so it's a rare process, but we measure it. I mean, it's not like these rates are inaccessible. It's just it takes a long time. The second bit of misery, so it's a real fun ending. The second bit of misery is that this amplitude will again interfere with this one, and lo and behold, the repeated theme of this half of the talk lecture is that this interference is destructive. So the bit that you want to measure, so the standard model prediction is here sorry, lambda is 1, so the standard model prediction is here. We see that there's this destructive interference between these two contributions, and so the cross section is reduced, around the standard model value. If I had large deviations from it, then maybe the interference pattern breaks and it becomes more easy to see, more or less. But the point is, it's a very hard process, and this is a very small part of the total. Right? The Higgs is a real background to itself here. So it's a hard thing to do, but experimenters are good at hard things. If we wait long enough, we'll get some constraints on it. Now, one of the interesting open questions in the standard model is that, guys, I told you that the Higgs potential was set in the standard model, and that's true. The problem is that it's set in a way which we have to be very careful of, because I write down this sort of formula here, and that's true, but I should probably be careful. I mean to say this is just from some tree-level result in terms of bare parameters. Right? Now, when I go to higher order in the theory, I have to renormalize my parameters, and that tells me that these parameters will run, and they will depend on all the other particles in the standard model too. So my Higgs potential, as I evolve the couplings, will change away from just this tree-level prediction. So the diagram I drew here is just a naive leading order diagram, and the full picture in the standard model is much richer. Now, if we think about what happens as the Higgs potential gets very large, then we can effectively say we're studying only the quartic term. Right? Because if this is a big thing, then raising it to the fourth power is much bigger than raising it to the second power. And so this would be my little bit down here where we know and love, where we explored. And this is some high energy unexplored region. Now, what could happen is that this could just keep growing forever and ever and ever. And we don't even see our little blip down here. And it's just a big wall. And in this configuration, we would say the Higgs potential is stable. Right? Nothing that interesting happens. RVev is the global minimum. But something interesting could happen is as I change lambda with my scale, if I make my scale large enough, lambda could become negative. And at that point, the potential would turn over and then will begin to become increasingly negative. That situation will be unstable and the Higgs vacuum will be unstable, meaning that given long enough time, there'll be some quantum tunneling that would take us from here outside of the stable region that would cascade down forever and very bad things happen. There's an even more interesting region where I have some region of instability, but then it corrects and becomes stable, increasing again. And then what would happen in that situation is that I get a second minimum at some very high scales. Right? If that was the situation, so if I had some region where it skirts the bound, it skirts with becoming unstable, but then restores itself, this will be called metastable. And this is a very interesting situation because here we see that there is a second vacuum that would correspond to a much larger VEV that would have a lower energy than our vacuum. Right, so in this situation, the Higgs potential will be called metastable. And these are some plots that show you, that was just my sketches, just I was playing with Mathematica. These are more actual calculations. And we see the various parameters that we can think of, the most important ones being the Higgs mass and the top mass, how they affect the stability of the vacuum. So this is a big bird's eye picture where we see there's a region of stability, metastability, and instability as a function of top mass and Higgs mass. But obviously, a lot of these values are just toy values. If we zoom in on where the standard model lives, we see we actually live in this interesting region on the boundary between stability and metastability. The most crucial parameter for the driving of the whether we're stable or unstable is the top mass, right? Because the Higgs mass isn't really going to change. It's sort of locked in around here now, right? But the top mass has a more interesting definition in the theory because it's a QCD particle, right? So the running of it is more complicated. And here we see the dependence on lambda. So when lambda drops down to 0 and becomes negative, that's when interesting things are going to happen. And we see as we get a lighter and lighter top mass, we have an increasingly stable lambda. And as the top mass becomes heavier, we have a region that pushes us deeper towards metastability. Now, you shouldn't panic about whether we're going to be obliterated by decay to a true vacuum. Firstly, because I'm reliably informed by cosmology friends that it wouldn't hurt, right? So it wouldn't be a bad way to go. First, number one. So, okay, so, you know, all got to go some way. Vacuum decay would be quick and painless. You might go like, what's that? If you're very observant, maybe. But it's okay. So it's not a bad way to go. Reason number one. The other more realistic thing is that it's very unlikely to have to actually be the way that you are going to go, because the probability of vacuum decay is very, 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 very small. Right? So this is happening at extremely high energies. So the quantum tunneling lifetime is big. Here we see vanishingly small probabilities. It's like the chances that one of my jokes will be funny. Right? That's the sort of level of things that we're talking about. And so here is interpretation of a couple of cosmological models, and they can tell you the actual lifetime of the universe, and we see that it's very, very, very long. So just nothing to worry about. But what is interesting, though, in a more thought-provoking way, is that this gives us an interesting theoretical region to study and to link cosmology with BSM physics, because any change in the Higgs potential at all obviously has huge effects on this, right? Because if I have an EFT, or that's going to give me a sixth order term, of course that changes the shape of the potential off the bat. If I have another singlet scalar out there that mixes with the Higgs, that immediately changes the form of the Higgs potential. So the Higgs potential is very easy to change in BSM models, which means that all of this in the standard model is just one landscape. But maybe BSM is saving the day and driving us down towards stability, and we don't even have to worry about the Higgs, the vacuum decay. So it's an interesting area to play with in terms of model building. All right, so now back to more LHC physics. So we have our Higgses. We want to understand whether the Higgs is coupling to all itself and its friends, so we can test whether the Higgs vacuum potential is our vacuum potential. Sorry, question?
Yeah, I have a very hard time.
Everyone's having a hard time. I mean, you make bad life choices. It's not my fault. Right?
It's this intuition that the vacuum of the vacuum expectation value of a field can tunnel. Because for me, the tunneling has a very clear interpretation when you think about like the way.
Right. I mean, when people talk about this, they're talking about classical field theory, right? Yeah. So the actual calculation is about what you should do. And you have to, yeah. So you can sit down and calculate the lifetime, but they're nearly always talking about, you know, classical field theory results, because it's one of those things where you're not going to get the Nobel Prize for it. Because if you're proven right, you've got, you know, depending on whether there's something else. So my colleague actually needs to be a stigma for this in the treatment. I'm not sure. But anyway, so if he was right, you might see it for like a brief signal, and but you haven't got time to stop very much. So the calculations of these things are often not done in some detailed quantitative field theoretical framework, because they don't need to be, right. The point is that there's this clearly interesting classical field theory result you can play with. So I think my answer is to look more. I don't want to belittle the calculations, but my interpretation is that it's done. The lifetime stuff is done more at that sort of level. But the runnings of the couplings, that's a real QFT calculation. So that is done, you know, 2 loops, fully fledged QFT to get the prediction for lambda, and then the interpretations in terms of this sort of stuff then becomes a bit more. Yeah, you're not going to be predicting that the universe is going to decay on April 24th. 1937. Right, so. Okay, good. Okay, so I'm actually measuring the couplings at the LHC. Right? How can we do that in a way which gives us an understanding of what type of BSM physics will be allowed, and how we can relate that to exciting things like whether the universe is going to decay or not. So the easiest thing you can do, and what was done in the early days of Higgs physics at the LHC, was just to work in what is called the kappa framework, where I would take any coupling in the standard model and I would just give it a kappa value. So this would be one for the fermions and one for the vector bosons. And of course, each particle will get its own kappa. So the prediction of the standard model is that kappa is equal to 1. So what's good about this framework? What's the pro about it? The first thing is that was why it was done in the early days of the LHC, is that it's experimentally easy to implement. You've got your Monte Carlo for the signal, you just scale it. So you have a very easy to use tool to make your comparison between theory and data. And it's also useful to get a very quick understanding of how the Higgs is working, right? Because if you look at these kappa limits, especially in the early days of data where things are confusing, and you see, okay, there's way too much tops, right? It looks like TT bar Higgs has been made, way too much. But then how does that talk to the other channels? And you can very quickly get a bird's eye picture where you see all of the kappas all together in one plot, and you see where the tensions are. So it has an advantage there, at least in the early days, it gives you that sort of quick information. Now, the bad things about the kappa framework is that it's not gauge invariant. So some theorists believe this to be a big deal. So breaks all physics. Think bad. There's no actual interpretations in terms of field theory, right? So if experimenters come along and tell me they found that kappa T is equal to 2, okay, great, thanks for that. It doesn't give you a clear interpretation of what BSM models I would favor, what it would disallow. It's hard work to say, okay, within this BSM model, you get exactly twice the rate of top, right? That's not the way it works. And the final thing, which is bad for everybody, this sort of thing, this sounds like it's bad for theorists, so experimentalists won't care. But this one is bad for experimentalists too, because everything is just a rescale standard model. So you never get any kinematic information. Right? You never say, oh, you should look at Higgs with high PT, or you should look at Higgs over here, because you give up that information. You just say, oh, it just looks a bit more like the standard model. So for these 3 very good reasons, the kappa framework is not really the desired one anymore. So that takes us on to what we have to do going forward. And one of the sort of the paradigms that we're shifting towards is interpretation of the standard model as some low energy effective field theory for some grandiose UV physics. So we have some UV physics at high scale, but that's much separated from the LHC scale. So we integrate out operators associated with this high scale and then get left over with the field content of the standard model. Now, what's nice about this type of setup is that you can start from a much more theoretically robust framework, because you can say, okay, I'm going to start with any operator that respects these gauge symmetries, but I'm going to allow them to now be higher dimensional, right? So you can start off with a gauge invariant field theory. You have to make a decision about how you're going to break electric symmetry, because if I'm allowing for different UV physics models, that's not always going to be necessarily the standard model electric symmetry breaking mechanism. But once I've agreed on how I'm going to break electric symmetry, then I have a set of operators that are induced in my low energy standard model effective field theory. So now what happens is that my Lagrangian becomes now my standard model Lagrangian that I know and love, plus a whole bunch of 6- and 8-dimensional operators, and even higher orders here too. And this is, again, a convention because you could add 5-dimensional operators, but then you would have problems with lepton number violation. All right. So the good thing about this is that it's theoretically extremely robust and very well defined, and you make a very clear set of statements about where your starting point is and what your ending point is. But once you've decided how you're going to set up electric symmetry breaking, the job is done. The bad thing is that there's a lot of these operators, right? So when I go over here in my sum, I have to go over, depending on how I set up my basis, around 60 operators if I meant to mention 6. And okay, that's bad, but it gets worse because in an effective field theory, the operators mix with each other. So they're not even each uniquely defined. They mix with each other at higher orders, so they become intertwined. So this makes it a much more complicated setup to do phenomenology with. So for example, this is just a few of them, right? So this isn't even proper SMEFT. This is joke SMEFT that I understand. This is where we look at just constraining Higgs anomalous couplings, right? So you just want to make some set of operators that allow you to parameterize the Higgs coupling to vector bosons in an anomalous way. And so you just see a whole bunch of operators. If you pick one, right? There's a dimension 2, there's a dimension 4, it's a dimension 6, And this is your mass depression here. It's written in terms of MW because it's the lambda is absorbed into this coupling definition here. But anyway, so you see the idea, right? There's a lot of things to measure here and constrain, and they all get messed up with each other too later on in higher orders and perturbation theory. So it has pros and cons in terms of its phenomenology. Okay, okay, so if we wanted to look at doing something with this as an example, let's think about what would happen if we were looking at, again, our favorite, Higgs to ZZ coupling, because this one is interesting to us because we saw earlier on that we have a way of measuring this at high energies. Right? So the question is, where do we see these type of operators? So here is the standard model, sitting right there. And then here is a bunch of EFT operators. And there's one little special one. This one here has a Levi-Civita tensor, and this one is a CP violating one too. So that's a special guy. If we look at the purple and green arrows and look at the momentum, we see each of them scales like roughly a factor of S compared to the standard model. So at high energies, when P is big, when I'm probing the vertex with high momentum, I am more sensitive to these coefficients, these operators, than at low energies. Right? Which makes sense because we know that EFTs will start to cause deviations at high energies that we saw already with our top mass example earlier on. And so if I'm in a decay, so I'm just decaying the Higgs to Z star, then my invariant mass is always around the Higgs mass, and presumably the new physics isn't around the Higgs mass, or else we would have seen it not in the EFT. So the one thing we know about the EFT off the bat is that lambda should presumably be much heavier than the Higgs mass. So looking in the on-shell region for EFT effects is never going to be the winning strategy. What we want to do is probe the vertex at high Q squared. So a good example for this, this is one of the things where there's millions of papers on it, but I have one that I understand, so I can steal from my own blog. So one of the places that you want to look at is associated production of a Higgs, because here you have an S-channel vector boson that you can give as much energy to as you can squeeze into at the LHC, and then you have that invariant energy is spread then between the decay products. They're able to probe an on-shell Higgs, but at high energy. So if you look at V Higgs production at large MVH, so a large invariant mass of the system, you get sensitive to EFT effects. And this is just an example plot here showing the sort of thing you could expect, where you have the standard model in gray because it's boring standard model, and then blue and red are just an example where we just pick one or two operators and turn on their effects. Because I'm always, you've met and realized I'm evil and mean after last night. This plot is also meant to show you how life is miserable, because here I can choose, because it's a multi-dimensional space, I can choose two operators such that there's a lot of BSM physics, but they mimic the standard model. just to make sure that everybody understands how brutal life can be. Right? So that means you have to measure a lot of different things, and you have to put it all together in doing your fits, right? The other thing we should always be aware of, because it's a school, is that we have to, when we're expanding out the amplitude in an effective field theory calculation, we have various types of contributions, right? So the first thing we have is the standard model. Then we have the interference of the standard model operator with the dimension 6 operator, so that gets suppressed by 1 over lambda squared. But we also have the contribution where the dimension 6 operator gets squared up together too. And that gives us 1 over lambda to the 4th. Now, this puts us into an interesting situation, because I can write a second thing that's 1 over lambda to the 4th, which is the interference of the standard model with the 8-dimensional operator. Now, we were already a bit worried, as theorists that have experimental friends, you would be worried that trying to do an analysis in the EFT is tricky enough because you have so many operators to constrain. Now, if I'm allowed to bring in 8-dimensional operators, at that point, we have thousands of these things, right, that all talk to each other. And so getting some kind of consistent picture with dimension 8 is an extremely large amount of work. Not impossible, just you're not going to get very good constraints on many operators that way, right? So you would like to be in a regime where you can ignore this and then focus on this. So one thing you could do is say, okay, what if I'm in a situation where this is small? and I just ignore this and this, and that would sound good. But even that has problems because sometimes this can become infinite, and you need to allow for the renormalization of these operators to get a consistent picture. So even that is not so easy. You can push yourself into a regime where you drop these terms completely. If instead of just worrying about the suppression scale, I also think about the coupling. And so if I look at the coupling patterns, I have GSMs, that would be QCD or electron weak couplings. And then I have potentially new physics couplings here, and I have them squared here and then back here again. So if I was in a regime where this term was much, much bigger than this term, then I could drop this term consistently and just have this prediction here. But I would have to bear in mind that in that regime, the new physics coupling is much bigger than the standard model coupling. So if I'm in a regime where I'm only including dimension 6 operators, then I should naturally be thinking I'm constraining strongly interacting models. Okay, so strongly interacting models of BSM physics. And of course, that's if you make this thing be true, then you're constraining super strong interacting models. Okay, so you can of course do these calculations and do these fits. These are a couple of old plots now that to definitely be updated. The point here is not to understand everything, but just to see that it's possible to do them. What you have to do is take a lot of data and do a global fit to the standard model from LEP data, from LHC data, and try to find all the things that are sensitive to these operators and vary them and see what you get in terms of rates. The important thing, I think, is a sort of message to take home is from Laura's plot here, is that the green smudges are the limits that you get on the operators when you do a global analysis. So you set up your Lagrangian, you set up all your inputs, you vary them, you test them, you constrain them, you get these constraints on the operators. That's like a consistent global picture. The purple one is when you just do each operator at a time, right? So one at a time. And of course, you can do much better constraints on operators when you individually constrain them, because you have bigger effects, right? You don't have things like I showed you before, they cancel out and that sort of stuff too. And so for experimentalists, this can be tricky because if you're doing an analysis and you want to constrain Higgs couplings and you're looking at a certain region, there's probably only a few operators that you're interested in, but you have to be aware of how everything is playing out in the bigger picture too. But I would say there's still useful information in the purple things on their own too, right, from a phenomenological point of view. So it's not like varying a few operators is so egregiously bad that you don't learn anything about like where lambda is. Right? So you have to be aware that it has to fit into a global picture, but I still think it's more dedicated phenomenological analyses are okay too. Okay, so although I think there was plenty of biased opinions before, now it's just getting, I'm well over time, so I'm just going to be like old granddad ranting at this point. Okay, so we are living in a tough time for physics, because if we think back to a long time ago in the 1930s, 1970s, there was a nice lamppost to look under, which was the W mass, right? So we knew that muons decayed, which gave us the full Fermi interaction. And from that, we could predict that there was going to be new physics, some kind of interaction at around the W mass scale. So we had an observation that mandated a new type of physics, and we knew the scale of that new type of physics because we knew the rate of muon decay. Right? So we could say that there has to be some new physics around the W or the Z scale, and that you should build a machine and look at 100 GeV. And indeed, that was found. In my first slide, we saw the discovery of the W and the Z at UA1, UA2. Now, this is tragic because I Googled modern lampposts like from the 1980s, and the description of this image was a very old lamppost, which as someone from the 1980s makes me sad that is now described as very old. I thought it'd be like, cutting edge, modern lamppost design, but there we go. Apparently 1980s is now very old. Anyway, so once you discovered the W and the Z, they give you the same problem again because you calculate their longitudinal scattering, and once more you have this high energy breakdown. So once more, there's a scale at which this unitarization has to happen. So physics tells you, look at the TeV scale, and you will either see strongly interacting Ws, which is a new regime to probe, or you would find something which fixes this problem, which is the Higgs. So you say, build your collider to probe physics around the TeV, and I will promise you something interesting will happen. Now, where are we, right? So if you are a fan of Star Trek Voyager, yeah, commiserations too. This is like the best episode ever because they're just bleakly sailing in this place with no stars, right? I think it's called the Void or something, and there's like some aliens that dump their trash. And anyway, it's like the whole point is that they're just in the bleak darkness and they have no idea where they're going. And that is effectively where we are now, because we don't have any more onset of unitarity violating behavior in the standard model. Standard model is unitary, and so there's no more no-lose theorems in the standard model. Now, before the LHC, the last 10 years, you clung to one which was naturalness. So the naturalness argument goes that I have to calculate the higher order corrections to my Higgs mass. I get various loop diagrams, the two interesting ones being this tab-poly one here and this top one here. And they conspire to have a quadratic divergence, which means that I have the dependence on my cutoff parameter lambda squared. Now you would say, okay, that's just I'm just calculating the relationship between the bare mass and my renormalized mass. That's always infinity. This is just infinity squared, not log infinity, and I'll renormalize it as best I can. But the naturalist problem is say, well, wouldn't it be nice if you didn't have this magic cancellation between these two very big numbers to get electroweak scale, right? So the naturalist motivation would be that, okay, mathematically it's fine to cancel infinities this way. But it's very different to how it works with fermions, which are protected by symmetries. And so if I put log of 10 to the 19 GeV, if I take the log of that, it just becomes 19 log of 10, which isn't that big a number, right? So when I put the fermion, if I put lambda in as my scale for the fermion mass, I don't get a very big correction to my bare mass, right? If I make the lambda be the Planck scale. Whereas obviously for a Higgs, I get 10 to the 19 squared, so I naturally predict a very heavy Higgs, right? So it has to be this delicate cancellation to get an electroweak scale Higgs. So the idea of naturalness is that this was a nasty thing to do. Wouldn't it be nice if you never had to do it? So when you calculate the Higgs mass at next leading order, we miss a piece, we put this piece in, and then the quadratic divergences cancel, and we're left with something which just gives us an electroweak star number. And then at this point, you wouldn't have to worry about, say, any weird cancellations that happen in the field theory. Now, the sad thing for naturalness is that LHC has killed it, right? Barring some models where you just only have particles here that don't couple to quarks or gluons at all, so you never get access through like a QCD type machine. So unless you're in some corner of a BSM model world where you can have no coupling to the particles that to give you LHC physics, then most sort of natural models like SUSY and things are killed as an argument because they are no longer at the TeV scale, right? So if I promote this to be too heavy, I just get what's called a little hierarchy problem, which is why is that scale, it's big and why is not big enough, right? So for this argument to work, it needs to be close to the electroweak scale, not too far away from it, right? So naturalness could still be saved by new physics at say 10 to 15 TeV, but it would also then start to cascade upwards, and then you would get a little hierarchy problem for the BSM physics, and so on and so forth, which maybe is just the cascading ladder to the exploration of the new physics sector, in the same way that the unitarity violation was the guide before, maybe is now its naturalness. So it's not completely ruled out, but it's certainly much less of a problem in that the mathematical problem is the same, but it doesn't look like nature cares. Right? It doesn't look like that the driving thing to new physics is not going to be that the Higgs desperately wants to be natural. So where does that leave us? So without a clear roadmap, it's challenging for us over the next 50 years to know what scale we should look at, right? We hope that if we build a 100 TeV collider, that somehow we'll have access to a scale where we see new physics effects. But I think as an intermediate stage, it's crucial to have a precision portrait of the Higgs boson to an unprecedented level of detail, so you can at least have an inclination about whether the Higgs potential is that of the standard model, right? So you want to measure the coupling of the Higgs to itself and to the other particles as best you can with a high luminosity LHC and ideally a lepton collider before you commit, to my opinion, to an energy scale, right? Because if you build a 100 TeV collider and there's nothing there, right? it's a big gamble, right? So anyway, I'm a very big fan of lepton colliders, and I think the next machine has to be a lepton collider. And you have to have an inclination of the scale. Otherwise, I'm not sure what the motivation is. Anyway, so on that happy note, here are some future collider. I'm very much over time, so I'll finish quickly. These aren't even my slides. I just stole them, and they're out of date, so I'll go through them very fast. The idea, the basic point is to show you that at a future collider, we can get very good percentage level constraints on our kappas. This is our bad kappa framework, but it's useful, as we said, for a bird's eye picture. It shows us the level of Higgs physics we can expect. We're talking about sub% level physics here. The other nice thing that is going to be unique to a lepton collider that we can't do a hadron collider is a direct measurement of the Higgs width. Right, so the LHC, we saw how we can measure it indirectly from constraining off-shell to on-shell couplings. A lepton collider, you can just do a recoil method where you just make a Z, and then you just look at the invariant mass of the final state, and you get the Higgs turn on, and then that is basically gives you a decay and sensitive way of measuring the Higgs. So from that, you can get the total rate independent of the width. And then finally, although I was a bit skeptical of a 100 TeV collider, I would still be delighted if they built one. And because there is still a rich Higgs physics program you can do, I'll leave you get access to these slides. I'm not going to read them all aloud. But the point is that, like the LHC, the 100 TeV collider will give you plenty of scope for Higgs physics. Okay, so the conclusions of my combined lectures is that the Higgs physics is now a mature program at the LHC, and you'll have a dedicated series of talks on the experimental measurements and results of the Higgs. So I stayed away from that as most as I could, unless it was to enhance my points. So you'll see recent Higgs measurements and cross sections later in, I think, early next week. And so we see that the program is very advanced and then progressing nicely. The main aim of the program is to get, I think, is to constrain the Higgs self-coupling. Once that is in any way constrained, we learn so much about BSM physics and the Higgs potential that we don't know right now. Most of the easy work on the theory side and the experimental side is done. So now any new cross-section you want to calculate involving Higgs boson is going to be a long calculation, longer than the lifetime of a PhD student. I mean, the PhD life, not the whole birth to death. But once we get to that stage, then physics is really in trouble. So the calculation, the theory is now very, very solid. There will be improvements, but there's not going to be any major shocks or changes, I think. The experimental thing is the same similar sort of way, and that's just a matter of maximizing the return that we can get on the investment. The main area of work, I think, on both the theory and the experimental side, is understanding how to work in the SNEFT and how to calculate and constrain in this model, which is not necessarily always super easy. All right, so I've totally run over time. I think we're still going to have the photo, but if you're looking too tired, there'll have to be too much like photoshopping to make you look smiling. So. All right, so there's time for a couple of questions. I'm not sure what the lighting in the rain is like. So.
Yes, thank you. Tonight we'll have the presentations today lecture, so I encourage you to ask questions now before the
like I said, running.
Yeah, so the webinar outside is good, even if it's sunshine.
Is that a question? Or okay, I have no idea.
Yeah, let's next question.
Yep.
So we've only got a fraction of the LHC data.
Yeah.
You understand our.
Yeah. Exactly. So okay, so the obvious one is the total rate, which comes into pretty much every measurement in some sense. And there it's pretty good. So the determining not just the problem that Higgs physics in general, but the more broader precision statement is that NQ glow PDX we needed, right, to match the NQ glow cross sections. So that's an obvious thing that we expect. You remember more than me. but we expect those to be reasonably close to the n squared limit. So there shouldn't be a big jump there, but it would be nice to have them confirmed. So dedicated extraction length for PDFs is an obvious thing on the bullet point list to confirm theoretical accuracy, but I don't believe it would change very much. I think it's just a checklist item to make sure we have it, we understand it, but it's not expected to be a big deviation from the n squared line. Then after that, it's often becomes an analysis dependent statement. So often you're looking at a very exclusive region, specifically a high energy. You probably worry about electroweak effects, right? Because if you look at high enough energy, the mass of the W and the Z is not a big parameter, and that means you can radiate them liberally. So you get an enhanced radiation of W and Z bosons, a little bit like what happens in the parton shower with gluons, right? And so at high energy, the electro-pseudoconf effects become relevant and can dramatically change the shape of effects. Now, often these are not included in things like the typical, parton shower match prediction. So their modeling of electroweak effects is going to be important, but that is very much a sort of analysis by analysis statement. So I'd say that it's understanding the interplay between your observables and your analysis, right? To answer the question. But there isn't, most, let's see, the Higgs, what would be nice, okay, so there's, so di-Higgs fully next to leading order with the full top mass would be nice. Plus electric correction, right? But then even then you see that the variance is not going to be the biggest player of di-Higgs, right? You don't have to measure it, then and then it has to get measured to the level of 20%, so before you worry about anything squared over it. So di-Higgs is not, BBF is known various approximations to NQ below. Gluon fusion and NQ UCP. So it's the toolkit of the theories is quite imaginative.
Well, it's probably saying this, but I think the mission of the LHC is in jeopardy if we are going to be in a position where we have certainly PDF uncertainties, but also electrically calculation uncertainties, modeling uncertainties, unable to get to the precision that's comparable what we're going to do in acquisitions, and that's a really important thing.
I agree, it's a very important thing. I would hope that it wouldn't jeopardize the mission, because I think that if it becomes well known and it's apparent that this is limiting, then it becomes like a trophy for theorists to hit, right? So this is where the dialogue between the phenomenology work is important, right? Because if it's known, theorists let out a target, right? You say this is a Lansing process wish list. You're like, what? It's not a wish list. So then you want to calculate it so that you can get the 1,000-side paper for the experimentalists, right? So I would say that I hope it doesn't jeopardize the mission, because if it's a reasonable, there's things that are reasonable and things that are unreasonable. If you tell me you'd like to have electrical corrections better included in your simulation tools, that's a perfectly well-defined problem that people can work on. If you tell me you want to get down to per mil level accuracy, then at that point I say, okay, good luck, But there's things that theorists can do given that time, and there's things that they're never going to be able to do at hadron collider.
Yeah, I didn't mean it as a charge. I meant it as a motivation.
Yeah, no, yeah, it's like, I would, yeah, we would hope to have that sort of motivation, because if there's not much for us to do, right? If everything is working perfectly, then we have to go find something else.